Today, the talk will be about astrophysics, and in particular, the monsters of the universe. The speaker will be Julie Hlavacek-Larrondo. Normally, we're very proud that we gather scientists from SLAC from all over the world, but in her case, things had to be gathered from all over the world just so that she could be born. She is the child of immigrants from two very different places who came to Montreal. She was educated in the French-Canadian system, went to Cambridge, did a brilliant thesis there on the structure of some active galaxies, came here to Kipac, the Astrophysics Institute of SLAC in Stanford, on an Einstein Fellowship. And she's been working with people here on X-ray observations of the biggest and most ferocious things in the universe. And that's what she'll talk to you about tonight. So let's welcome Julie and hear about the monsters.
Thank you. Okay. Can everybody hear me? Yes, right? Okay. So hi, everyone. I'm really happy to be here. And so today I'm going to be talking about the most powerful and mysterious objects in the universe. Okay, and it's because of their power that I call them monsters. Basically, what I'm going to do is I'm not going to tell you exactly what these monsters are yet. Okay, instead, let's pretend for now that they're basically dragons. Okay, and instead, what I'm going to do is I'm going to tell you a very interesting story about a very special object, one of these monsters. And what we'll do is we'll go through the steps that astronomers did decades ago when they discovered this object, and we'll piece together all the clues, and finally we'll come to the conclusion to see what these kinds of monsters are actually. Okay? And so to start off, basically we're going to go on a small journey. Okay? What we're going to do is we're going to take our telescope, so any kind of telescope that we want, and we're going to point it to a very particular region in the sky. Okay, so not just any one, but one in particular. And this region is called the Cygnus constellation. Okay, so this is where our story takes us. So this constellation is quite a well-known constellation in the northern sky, so we can actually see it from here. And it's based, so it's a lot of these stars that come together, so the constellation is traced out by these green lines here. What's interesting is perhaps there's this very bright star here, which happens to be the 19th brightest star in the sky, so quite bright, but this is not where we're going to focus our attention to. What we're going to do is we're going to focus our attention here, on this particular star called Eta Cygni. Okay? And what's actually interesting is that we're going to zoom in this part of the sky, so let's do this right now. Okay? If you have a very nice telescope, this is the kind of image that you'll see of this region of the sky. And as you see, it's a very beautiful image. It's made up essentially of a lot of stars. You have a lot of activity going on, a lot of newly formed stars that are happening. But there's actually something very different that's going on in this region of the sky. And what's different is based on a discovery that was made in the 1960s. What happened in the 1960s was that astronomers launched rockets that for the first time observed the universe in X-rays. Okay? And they didn't know what they were really going to see, but they found that in this region, there happened to be a very, very bright X-ray source. And this source was named Cygnus X-1 because it was in the Cygnus constellation, and it was the first X-ray source discovered there. Now, what I'm going to do is I'm going to show you where this source is. So the X-ray emission isn't actually coming from all over this region here. It's only coming from one very, very tiny region, from here. Okay, so where this red little square is. It's coming from this very tiny region, and just to give you an idea of what we're looking at, this is what we would see in the X-rays. Okay? This, as I said already, this is one of the brightest X-ray sources in the sky. Now, the problem with this is that for an object to emit X-rays, it takes a very particular kind of situation. So not all objects actually do this. Only a very small percentage of them do. And to be able to emit X-rays, you basically need the object to be extremely hot. Okay, how hot? I'm going to explain this maybe in a bit easier way, yes? So this is a very typical explanation for what's happening. So basically what you do is you take your oven, your stovetop, and when you turn it on, so initially it's black, but as soon as you turn it on, it gets heated up, and then it starts to glow. Okay, it starts to glow red. And what's happening is that objects basically are going to emit a certain kind of light depending on their temperature. All right, and just to give you a better understanding, this is basically what happens. So depending on the temperature of the object, you get different kind of light that it's emitted by the object. So what happens here in the case of our stovetop, as it goes up to about 400 degrees Fahrenheit, it's mostly going to emit emission in what we call the infrared. So we're going to get a lot of light in the infrared, but some of it is actually going to go all the way up to the visible, into the red portion here. And so our eyes are actually not very sensitive, and they can only catch a glimpse of what's happening. So our eyes can only see what's happening in the visible. However, we can use telescopes to try and probe these different regions here. So radio, infrared, up to X-rays. And so I'm going to focus today on this part here, so on the X-rays. Basically, what this is telling you is that for an object to actually emit X-rays, you need it to be extremely hot. So we're talking about several millions of degrees Fahrenheit. So very, very hot. So whenever you look at something in the sky that's emitting X-rays, it's basically telling you that something very hot, something very energetic is happening in that particular region. And so coming back to our object before this, basically what we do is we use these telescopes, and so I'm going to talk about this telescope here. And so coming back to our object, so basically it emits a lot of X-rays. So what's happening? What's making it so hot that it's actually doing this? And recalling that this is one of the brightest sources in the sky, so it has to be extremely energetic in this region. And all of it is coming from this very tiny square here. And so what astronomers did was when they figured out that most of this X-ray emission was coming from this little square, they said, okay, let's try and see what's actually there. Is there an object? Is there, for example, a supernova remnant? And so the reason why they thought about supernova remnants was that at that time, they knew that supernova remnants actually emitted X-rays. And so supernova remnants are basically what's left over once a very massive star has exploded. And so you see these beautiful supernovas. And so they said, maybe that's what's happening here. Maybe that's what is emitting all of these X-rays. So they looked for one, and they didn't find one. Okay? What they found instead was a very massive star. Okay? So this is part of a diagram that was taken from the original paper. So these were one of the discovery papers back in the 1970s that found this massive star to be associated with this X-ray emission. And so they derived the masses of the stars. So we're basically talking about a very massive, so essentially between 15 to 30 times the mass of our sun. So a very massive star. However, the problem is that astronomers knew at this time that when you looked at other stars that had the same kind of mass, they didn't emit that much X-rays. Okay? They emitted about 1,000 times less than what we were seeing. So something else, something different was happening here. What they also noticed is that this star was moving. It wasn't actually stationary. And it was moving in a very particular way. It was moving just like this, as it's illustrated in this diagram. What this diagram shows is the speed of the star that's coming towards you or receding from you. So basically, what you do is you go on this plot here. As it goes up this curve, as the velocity becomes positive, it basically means that the star is going towards you. And as it's going down, it's going away from you. And it's repeating this motion, towards you, away from you. So when astronomers see this kind of diagram, they become really excited. Why? Because this basically means that this star is part of a binary system. Okay? What do I mean by binary system? I basically mean that this star is in orbit with another object. For now, we don't know what this object is, and the two are orbiting around each other. Okay? And this is causing the star to move here in this orbit. And so for now, let's just focus on this movement of the star, and I'm going to explain this diagram a little bit more in detail. So what's happening is that as the star orbits in this direction, it's actually going towards you. Okay? So the star is up here in this diagram. But as it moves in the diagram, at this point, it's not going towards you or away from you, it's just going from left to right. Okay? So it's here, it has a velocity of 0. But as it continues in its orbit, in this phase here, it's going away from you. And you continue and continue, and this is what happens, and this is why you get this kind of diagram. So this is why it means that this system here is part of a binary system. But the question is, with what? What's the other object? Okay, so we know that these massive stars, as I've mentioned, do not really emit a lot of X-rays. Okay, so this basically means that perhaps the X-rays are actually coming from the other object here. Okay, so what is it? Could it be a star? Could it be some other kind of exotic object? We don't know for now. But what astronomers did know is that when they looked at this diagram here, okay, they can actually calculate just how massive the other companion has to be, because the intensity of the velocity, so how fast the star is orbiting around the other object, and the period here of this diagram basically tells you a lot of information about the system. And it tells you the information about the other object, so just how massive this one is. And what they found was something quite interesting. They found that this object was very massive. Okay, we're talking about at least 3 times the mass of our sun, at the very least. Okay, so this meant that technically it should be maybe some kind of other star, and yet they weren't seeing it. They could see no kind of signature of any star emission. So what was going on? So this was part of the second clue. Okay, now the third one is that when they studied the X-ray emission that was coming from this object, they actually noticed that it was varying. So yes, the source was emitting a lot of X-rays, but this kind of emission was varying quite significantly. And when they looked at it in even more detail, the kind of time scales, we're talking about microseconds. So on microseconds, the source, the amount of X-rays it was emitting, was varying by several factors. Okay, so a very huge amount. And this is a problem in astronomy. Why? Because it tells you that essentially the object, the size of the object, has to be quite small to be able to vary that quickly. Because the time it takes for the information to go from one end of the object to the other, it depends essentially on just how fast you can transmit that information. And the fastest thing that we know of is light. Okay, nothing can go faster than light. It travels at about 200,000 miles per second. It's extremely quick. And so that limits just how fast the information can travel, and so how small your object is, because we know it's varying on microseconds. All right? So this basically told astronomers that the object, to be able to vary this quickly, had to be very small, so that the information could go from one end to the other. And so the question is, how small? So they calculated this, and what they found was that the object had to be very, very tiny. We're talking about hundreds of kilometers wide. Okay? And there are only 3 things that we know of in astronomy that can be extremely small, yet extremely massive. And these 3 things all come from the death of stars. Okay? So the first kind of object is a white dwarf. So what happens is that you have so if you have a very normal star, for example, a star that's about the mass of our sun, this star is basically burning fuel in order to fight gravity. But the problem is that stars can't burn fuel forever. They run out at some point. And so at some point, gravity wins, and everything collapses. And so what you get for a star that's like our sun, you end up with something that we call a white dwarf. So basically, you have this kind of object. Now, the problem with white dwarfs is that we know that they're actually much bigger than hundreds of kilometers. They're typically thousands of kilometers wide. And so basically, white dwarfs are too big to explain this object. So astronomers said, no, it's not a white dwarf. The second object they examined was neutron stars. Okay, so neutron stars are, what happens is that if you have an even more massive star to start off, this one collapses into a white dwarf when it dies. But at some point, since the mass is so big, even the white dwarf can't support the pressure of this mass, and then the white dwarf ends up collapsing and forming a neutron star, so an even smaller object. And we know that neutron stars are typically 12 kilometers wide. So yes, they're quite small. However, we astronomers know that neutron stars can only go up to a certain mass. They can only be up to about 3 times the mass of our sun. Okay? If it's above that mass, what happens is that gravity wins over again. There's too much gravity, the star collapses even further. And so what do you get? You get a black hole. Okay? And so basically, white dwarf was too big. Neutron star, it was impossible because they knew that the mass of this object was more than 3 times the mass of our sun. So the only possibility they were left with was a black hole. And so what is a black hole? Well, by definition, this is what a black hole looks like. Okay? Essentially, black holes are objects so compact that nothing can escape. Gravity is so strong that even light cannot escape. That's why they're called black holes. But in terms of its size, there is a definition of just how big black holes can be. So this is what we call the event horizon, which measures the radius within which nothing can escape. Okay, so within this radius, not even light can escape. That defines the size of a black hole. It's approximately given by what we call the Schwarzschild radius, which is given by this equation here. But I won't go into detail about this equation. But just to give you kind of an order of magnitude, if you take something that's as massive as 3 times the mass of our sun, so something similar to what we were seeing in Cygnus X-1, then the size of the black hole is tiny. We're talking about 9 kilometers. So black holes are extremely compact, massive structures, very powerful. So this is what astronomers thought was going on here. And so, but the problem is that I just told you that black holes don't emit light because nothing can escape from it, not even light. But we know that this object here was emitting a ton of X-rays. So what's going on? Well, what happens is that these two objects are so close to each other, they're orbiting around each other so quickly, they're so close, that the black hole is literally tearing apart the star. And just to show you what this kind of looks like, so this is an illustration of what we think is going on. So you have a gigantic, massive star, and you have the black hole here. And basically, the two are so close to each other that the black hole is literally tearing the star apart. And as it does this, it drags material. Material starts circulating, forming what we call an accretion disk, which will eventually be accreted onto the black hole. And as material settles into this accretion disk, what happens is that the material here is traveling very quickly, okay, almost at the speed of light. It's being attracted by this immense gravity that's created by the black hole. And as material does this, there's a lot of friction that's created. So the material essentially heats up due to this friction. It's very similar to what you do when you rub your hands together to try and get them warm. This is the same thing. There's friction, it heats up. But the friction is so intense that it heats up to, we're talking about 20 million degrees Fahrenheit and even more, so extremely hot. And this is why this source here is beaming in X-rays. This is why it's so bright in the X-rays. And this kind of object, this is what I call a monster, something so powerful that it can literally tear up a star. Although, as we saw, the size is tiny. So very, very tiny. We're talking 9 kilometers wide. So this is what's going on. Now, astronomers in the last couple of years have studied this object quite intensively. And now we know that the star here, we have a very precise estimate of its mass, about 20 times the mass of our sun. And this black hole is actually 15 times the mass of our sun. So very massive. And so this is the kind of object I'll be talking about for the rest of this talk. And so just to give you kind of a glimpse of what I'm going to talk about, so I showed you one example of one kind of black hole that we see. These are what we call stellar mass black holes. So they're remnants, basically, of the death of a very massive star. So we're talking about an initial star that had about a mass of 20 times the mass of our sun. And this collapsed due to gravity when it no longer could burn its fuel. And so these kinds of stellar masses, black holes, typically have this kind of mass. However, what I'm going to talk about for the rest of the talk is what we call supermassive black holes. Okay, so these are black holes that are gigantic. They're at least 1 million times the mass of our sun, so huge. We essentially think that almost all galaxies have one of these monsters at its center. Okay, so I'll talk about this. And then finally, I'm going to talk about the kind of research that I do. So I work on these supermassive black holes, but I actually work on the biggest ones that exist. Okay? And so I'm not going to tell you just yet how big they can actually get. I'll tell you that at the end. But basically, this is the kind of object I study. So really, really big supermassive black holes. And so let's go and move on to this kind of object. And so we're going to take another journey. This time we're going to go somewhere very different in the sky. And just to give you an idea of where we're going to go, so basically this is a very nice illustration of what we think our own galaxy looks like. Okay, so we are part of a galaxy called the Milky Way. It's very difficult to know exactly what it looks like because we're in it, and so it's difficult to see what it looks like from outside. But this is the kind of picture we think it looks like. And so you have these beautiful spiral arms. The Milky Way is basically a spiral galaxy. This is where we are located here. Okay, so we're approximately 26,000 light years away from the center. And what I'm going to do is I'm going to focus here, right at the center here. This is where we're going to look at. And as we'll see, there's a very interesting monster right at the center here. And to kind of show you what this monster looks like, we're going to use the Chandra X-ray Observatory. So this is a very, very nice telescope. This is one of the telescopes I use for my research. It was launched in 1999. What's really amazing about this telescope is that it significantly increased the resolution of X-ray images. It went from a factor of about 10 when it was launched. So it was 10 times better resolution. And I'm going to show you just an idea of what kind of improvement it made thanks to this telescope here. So if we take a picture of the center of our galaxy, so we focus our camera here, right at the center. This is what we would see before Chandra. Okay, so you see before Chandra there's some structure, but you don't really know what's going on. Now I'm going to show you what you see with Chandra. This is what you see. Okay, so this is the amazing thing about Chandra. It's kind of like the Hubble, but for X-ray astronomy. We get amazing images out of it. So this is a very, very deep image of the center of our galaxy called the galactic center. Okay, so basically what this means is that imagine you took your camera, okay, and you took a picture of the night sky, but you open the shutter and so that it collects lights for over 26 days. This is how long this exposure is. So it's a very, very deep image. You can see a lot more objects the deeper you go. And so you see there's a lot of structure here. And I'm going to talk about 2 or 3 of these and then focus on one particular object. So there are interesting structures here. So for example, this structure here, which is called Sagittarius B2, happens to be a very cold molecular gas. Okay? And we know that cold objects don't really emit X-rays, and yet it's showing up in this image. So what astronomers think is going on is that this amount of cold gas is actually being illuminated by all of the X-ray photons that are coming here, so all of the X-ray light. And as this light goes to the molecular cloud, it gets reflected, and that's how we see it light up. Okay? So this is an interesting structure. Another interesting structure is here, which is called 1E1743. This is one of the another candidate. So we think that what's actually going on is that there's another binary system here, consisting again of a black hole and a very massive star. So this is another candidate. And we know about 30 systems of these in the Milky Way. Okay, so Cygnus X-1 isn't the only one. There are about 30 other candidates where we think there's a black hole that's tearing up a very massive star. Here you have another interesting structure, which is basically a bunch of massive stars that are all packed together due to gravity. So that's interesting, but I'm going to focus here. Okay, so this is a very well-known object called Sagittarius A. And as you can see, it emits a lot of X-rays. So let's zoom in right on this portion here. Okay, so very tiny, but let's zoom in there, and let's see what it looks like in the X-rays. So this is what you get. Okay, so the same square here is the same region as we were seeing this tiny square here. So we're zooming in quite significantly. This is an even deeper Chandra image of the very, very center, so the very galactic center. It's over 34 days of exposure, so ultra, ultra deep. And we can see a lot of structure. But we can see in particular one object here, which stands out. And this is what we call Sagittarius A star. So let's zoom in even more. So you can do this with Chandra. And what you see is there's this fuzzy cloud here. Now what's really interesting is that astronomers found that what was actually happening is that a lot of this gas was being expelled. Okay, so something was expelling the gas. And so the idea that you can get is there's actually one supermassive black hole at the center here that's secreting material, but that is also expelling a lot of material. And the reason why we think that it's a supermassive black hole is based on a very important discovery that's been made over the last 15 years. And it's a discovery concerning the galactic center. Okay, and I'm going to show you this discovery here. And so basically what they did is that astronomers observed the stars at the center of our galaxy, so on Sagittarius A star. And this is what you see here. So all of these fuzzy blobs are individual stars. Okay, and what we'll see is a video that was made over the last 16 years. Okay, so it's a lot of data. These are the real images. So it's not a simulation. This is really what you see. Okay. And so just to show you, I want you to focus in particular on this star here. Okay, as you'll see. So the stars are going to move. And this is what you see. Okay, so the video is repeating over 4 cycles and zooming in each time. And so what you see is that the stars are moving. Okay. But what's really incredible is that this one here is moving very quickly. Whoop, and then it goes back up. And then it goes back up. Okay? What's happening? So basically you have a star that's going in essentially an orbit. It's orbiting around something. It's orbiting around something that we cannot see, that's black. Okay? And so very similar to the way astronomers worked on Cygnus X-1, based on just how fast the star is moving about this invisible point, you can calculate the kind of mass that has to be there of this object here that's essentially black. And when you do this, the kind of mass that you get is 4 million times the mass of our sun. So gigantic. And so we're talking about an extremely massive dark object. Now, the other interesting thing is that if you look at the kind of scales you're dealing with, so when this star actually approaches, there's kind of like a beeping. Is that okay? Okay. I will ignore the beeping. And so when this star actually approaches here, okay, the kind of distance it reaches is about 6 light hours. So it's very, very tiny. Just to give you an indication, 6 light hours corresponds to approximately the size of our solar system. Okay, so it takes light about 8 minutes to reach, to go from the sun to Earth. Okay, and for 6 light hours, it's approximately the size of. Oh, that is not me. Okay. So this is a black hole. Yeah. Okay. And okay, so I'll continue a little bit. So this is one of the really the strongest pieces of evidence that we have for the existence of an invisible object that we cannot see, extremely massive, a supermassive black hole. Okay, so 4 million times the mass of our sun. All of this has to fit inside the the scale of the solar system. So very, very compact. And so people have been taking these data for over 16 years now, and they've actually measured the orbits of about a dozen of these stars. So they get a very, very good constraint on the mass of this object. And I'm going to show you other interesting pictures very soon. It started beeping. Okay. 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 And so I'll show you a picture as soon as this comes online of something that's happening now. That's very interesting about Sagittarius A star, so the supermassive black hole at the center of our galaxy. There's actually a cloud that's approaching this black hole. Okay. This cloud is named G2. And we've known about this cloud for a couple of years now, and so we've seen it approaching this supermassive black hole. And actually now, this year, this is when this cloud is supposed to interact with the black hole. And so we'll be able to see exactly how black hole accretes mass. And this is going to be an amazing opportunity. And I'm going to show you a picture very soon of this cloud that's actually approaching the supermassive black hole. and we can just about now we can start seeing it being torn apart. Okay, but stay tuned for the results because this year is going to be extremely exciting concerning that. And at some point, I will show you this. Okay, so there are two leading theories. So one is either gas, okay, but there's actually a group that published a paper about a year ago that suggests that this cloud is actually a star. Yes, so we don't have the technology to resolve the cloud, so we don't know just how small it is. For now, we just see a fuzzy image. But we'll see once it interacts with the black hole, because that will be very different if it's a star or a cloud of gas. So we will see. It's starting to, we can see it kind of starting to spread out. We can't resolve it, but we can see that the velocity has been changing. And so this is consistent with it being torn apart, although we can't resolve the cloud. But yeah, let me take questions. Okay, thank you.
If instead of collecting data on X-rays, as you did
Yep.
the one that you're focusing on, if you collected data on some other part of the spectrum,
Yeah.
what would you, or is anybody doing that, and what would you see?
Yeah, so you see very different things. Oh, yes. Okay, so I showed you a picture of what the galactic center looks like in the X-rays. And so the question is, if I understood correctly, what it looks like at other wavelengths. So there's actually a very interesting discovery that was announced about a week ago about an image taken in the radio. Okay, and what you see, yay, okay, cool. And I'm going to show you that image, and then I'm going to come back here, okay? So, okay, so this is the image. So basically, what you see in the purplish colors this time is the X-rays, okay? So you see the same structure as before, but in the radio, here you see a lot of this kind of weird material here, and there's actually something very faint in the X-rays here that you may not have seen initially, but there's a jetty structure, okay? And what they're suggesting is that there's actually a jet coming out of the supermassive black hole. It's interacting with material here, creating a shock front, and this lights up in the radio, okay? This is a very new discovery. So we'll see if this actually works. Yeah. But coming back, and I'll take more questions at the end. Yeah. And so let me show you just one more time this video, because it really is amazing. And so you have all of these stars orbiting, and then in particular this one. And so these, again, are the real images. So there are a lot of simulations out there, but this is the real thing. This is really what's happening. And concerning the cloud G2, this is basically what we see. Okay, so this is a zoomed-in version of the previous figure. These are the individual stars. Okay, so we can't actually resolve the stars, so they're just fuzzy blobs. And this is the cloud. So we can track its movement from 2006, 2010, 2013. The black hole is located approximately here. Okay, so it's starting to interact, and then it's going to do something very amazing. We're still not sure how it's going to react. It might just flip over. We don't know. We'll see. Okay, but time will tell. Okay, so it's very interesting. But this is what's happening now. Sorry. Okay. Okay, but although Sagittarius A star, so the black hole at the center of our galaxy, is very interesting, it's actually what we call very quiescent. So there is some activity, but not that much. Okay, and there are other black holes, what we call active black holes, that are very different. These are the exciting ones. Okay, these are black holes that are accreting a lot of material, and what's happening is that in some black holes, they're able to emit what we call jets. Okay, and these are jets made of relativistic particles, so particles that are very energetic. What's very strange about these jets is that they seem to be extremely thin. Okay, and one of the ways we explain this is that essentially what's holding them together, what's making them so thin, are magnetic fields. Now, when you take, if anybody's done a physics class, okay, if you take magnetic fields and you take relativistic particles, and these relativistic particles are accelerating in a magnetic field, what do you get? You get what we call synchrotron emission. Okay, so this is a very typical kind of emission that we see in the universe, and basically synchrotron emission peaks in the radio. So when astronomers study these kinds of structures here, they use, for example, Chandra to study the hot gas that's on the accretion disk that's heated to millions of degrees Fahrenheit, but they use what we call radio telescopes to study these jetted structures here. Okay, so although radio light isn't very energetic, it indirectly traces very energetic particles that are accelerating in magnetic fields. And so we use a combination of these two kinds of telescopes to understand these objects. And this is basically what I do for my research. And so I'm going to show you some examples of these active black holes. Okay, now to do this, we have to go on, we have to look at this in a very different region of the sky. So not at the center of our galaxy, not towards the Cygnus constellation, but what we're going to do is we're going to go away from the galaxy. Okay, so our neighboring galaxy is called Andromeda. It's located approximately at a distance of 2 million light years from us. But what we're going to do is we're going to go 10 times further than that. Okay, and what we'll hit a very interesting galaxy called Centaurus A. So Centaurus A is the galaxy that contains the nearest active supermassive black hole. Okay, and we'll just see how powerful this kind of object can be, this kind of monster can be. And so this is a beautiful optical image, okay, of the galaxy. What you see is very typical. This is a very large galaxy. This kind of stream here is essentially dust, and so dust absorbs light and prevents us from seeing what's happening at the center. So this is typically what you see. However, if you look at the same exact image, this time in the radio, we're calling that radio allows us to trace these jets of relativistic particles. This is what you see. Same image, but in the radio only. You see something completely different. Okay? This is why it's so important to combine different kinds of lights to try and understand what's going on. This is why astronomers use all kinds of telescopes to try and understand the physics behind what's going on. And so just showing you this image again. This is the radio. Now what I'm going to show you is the same exact image, but this time in the X-rays. This is what you see. So this is a beautiful image taken again with the Chandra X-ray telescope. You see something totally different. You see, yes, the jets light up in X-rays. You see these beautiful interactions here that are lighting up in the X-rays, but you also see a bunch of point sources. Okay? We think that a lot of these points are actually some of these binary systems that I talked to you about, where you have a stellar mass black hole and a massive star, and the two are orbiting close to each other, and the black hole is shredding the star. This is what we think at least some of them are doing, but you see something completely different. And so combining all of these together, this is a picture that we can build. We have a very massive galaxy. Okay, so a galaxy typically is maybe 50,000 light years across. Okay, so it takes light 50,000 years to cross it. And what you see is that you see these beautiful jets that are on the scale of the galaxy, so gigantic jets, and these are being created by one single object, by one single supermassive black hole at the center of this galaxy. Okay, so this is the power of black holes. Although they're tiny in size, they're literally about 1 billion times smaller than the size of the galaxy. Although they're tiny, they can create enormous structures, extremely powerful. They can have a very important impact on their surrounding medium, and by extension, their galaxy. Okay, and this is the kind of thing that I study. However, there are black holes that are even more active than this. Okay, so this is just one example, and we'll see the things that are even more powerful. And to do that, we have to go somewhere else in the universe. And what we'll do is, first of all, I'm going to show you what the universe looks like. Okay, so I'm going to show you one of my favorite images. And so this is a very nice image taken from the Sloan Digital Sky Survey. Basically, what it did is that it looked at the sky, and it said, I'm going to count all the galaxies in the sky, and I'm going to place them on a diagram. So every single point you see here represents one galaxy. And we're calling that each galaxy contains billions of stars. Okay, so this is how big the universe is. This is huge. And just to point out, this kind of scale is only a tiny, tiny, tiny fraction of the actual universe. The universe goes beyond these kinds of light years. Okay? So this is very, very tiny. And yet you see that there are a lot of galaxies. And what's interesting is that you see that these galaxies aren't randomly distributed. There's actually structure. There are these very beautiful filaments here, okay? And these filaments tend to meet up in what we call clusters of galaxies, okay? Now, before I get there, I want to make one analogy that the reason why this has been always so interesting to me is that it reminded me a lot of what neurons actually look like in the brain. So you see just neurons here and then connection by the filaments. And so it's very similar what you see in outer space. So to me, this has always been something very impressive. But I'm going to focus on these clumps here, which are called clusters of galaxies. And I'm going to show you one example, one very famous example of a cluster. So basically, clusters of galaxies consist of hundreds to thousands of galaxies that are bound together by gravity. So this is one example here. This is one of the most massive clusters that we know of, containing thousands of galaxies. And so you see all of these yellow points here represent a galaxy. So this is a beautiful image taken with the Hubble Space Telescope. Now what I'm going to do is I'm going to show you what we see in the X-rays. Okay, so recalling again that X-rays traces very hot, energetic phenomena. So the exact same image, this time in the X-rays. Okay, I don't know if you were expecting that, but basically what this means is that clusters are actually X-ray sources. Okay, so it's not only the accretion disks around black holes, but clusters are also X-ray sources. So why is this? And so just combining these two images here. And so to try and understand this, I'm going to recall that basically when we look at X-rays, we're looking at things that are very, very hot. So we're talking about at least 20 million degrees Fahrenheit. Okay? And the reason why clusters happen to be very X-ray luminous sources is because they're very massive. Okay? So we're talking about the most massive gravitationally bound objects in the universe, these clusters. And because of that, whenever a gas falls into the cluster, it gains a lot of energy because of the potential well. And as it does this, it gets heated up to extreme temperatures. It gains a lot of velocity. This translates to a very high temperature gas. And so much, they're so massive that the gas gets heated up to about 20 million degrees Fahrenheit and even higher. Okay? And it's simply because they're extremely massive, and anything that falls in there is going to gain a lot of speed, it's going to get heated up, and it's going to emit a lot of X-rays. And so this is some of the objects I've been studying. And the X-ray emission actually tells us a lot about what's going on. And I'm going to show you two typical examples of what we see of the X-ray emission in clusters of galaxies. And so the first one is a very famous cluster named the Bullet cluster. Okay, so some of you may have seen these images. And so the Bullet cluster was discovered several years ago. And it's very interesting because what you see is this is an optical image, so it traces the galaxies. You see there's a bunch of galaxies that seem to be kind of linked here, and then there's another group here. So what's going on? So basically, what I'm going to show you next is the same image, but in the X-rays. This is what you see. Okay. So what this tells us is that, yes, okay, clusters emit X-rays, but there's a lot of structure going on here. There's this very weird shaped structure here. And what this actually looks like is what we call a shock front, very similar to what happens when a bullet goes through the air or water, creates a shock front here. Okay, so what's happening, okay, basically in this cluster here is that initially this massive structure consisted of two smaller clusters of galaxies. So one cluster that contained these galaxies and another one contained these galaxies. Now what happened is that when these clusters collided, okay, so they literally collided against each other, what happens is that the galaxies are what we call collisionless. So it's very rare that two galaxies are going to directly hit each other, and so they're just going to pass through. Okay, so galaxies just pass through. And so what you see is one bunch of galaxies here, one bunch here. So they just pass through. However, the hot, what we call intracluster gas, the one that you see in the X-rays, is not collisionless. This gas will heavily interact. Okay? And so what happens is that at some point, one of the clusters went faster than the speed of sound, broke the sound barrier, and created one of these shock fronts here. And this is what you're seeing. So very similar to what happens with bullets. Okay? But we're seeing this on astronomical scales. Okay? So it's really gigantic, gigantic scales. So we're talking about much, much bigger than the size of an individual galaxy. Now, the other kind of structure that we see that I'm very, very interested in, okay, so again, this is based on the X-ray emission that we see in clusters of galaxies. So to show you this kind of emission, I'm going to focus on one of my favorite objects, which is the Perseus cluster. So the Perseus cluster is, again, a very massive cluster of galaxies, contains hundreds to thousands of galaxies, all bound by gravity. The center of the cluster is actually located here. Okay, so this is a beautiful image, very big cluster, but the center is here. And as you can see, there's something very strange going on with this galaxy. It doesn't look like the other galaxies. So what we're going to do is we're going to zoom in right here on this galaxy. So this is what we see. So this is the central galaxy in the Perseus cluster. Okay, so again, Perseus cluster contains hundreds of galaxies. And basically what you see is you have a lot of structure. Okay, and you see these beautiful filaments here. And a lot of people, including here at Stanford, study these filaments because it's very difficult to explain how they got there. But I'm going to focus on what we see in the X-rays, okay, because we're tracing the hot universe. So the same image, but I'm going to show you in the X-rays. So we definitely should see some kind of X-ray emission because we know clusters emit X-rays. And so this is what we see. Okay. So again, I don't know if you were expecting this, but this is, for me, one of my favorite images. Okay, and I'm going to explain what's going on. So this is the X-ray emission in blue. Okay, so you see a lot of X-ray emission. This is coming from the hot intracluster gas, but you see a lot of structure here, here, here. Now what we're going to do is we're going to look at the same image, but I'm going to overlay what we see in the radio, because maybe this is going to tell us a bit more information about what's going on. And so this is what we see in the radio. So the pink blobs are where all the radio emission is coming. Now recalling that the radio emission is a very good indicator of synchrotron emission, so the emission coming from the jets created by a black hole. So what's actually going on is you have the central galaxy. This galaxy here contains a very active supermassive black hole. This supermassive black hole is creating jets of relativistic plasma that we see in the radio. But as these jets propagate through the hot intracluster gas, they literally push the hot gas away. Okay? So they're literally just pushing it away, doing work against the medium here. And this is what we're seeing. So you have the black hole, jets, and they're pushing all of this gas away. And these are what we call bubbles in astronomy, or X-ray cavities. And this is the kind of object that I study. Now, the reason why this is so remarkable is that before, if we did not have the X-ray information, if we only had the location of the galaxy here and only the radio, we wouldn't know how the radio actually affects the surrounding medium. Okay, because we still don't understand exactly what jets are made of or how they're made. However, we see through the X-rays the actual work that the jets are doing on the medium. So we literally see that they're pushing it away. And so we can quantify just how energy you need to literally push away this amount of gas. Okay? And just on the scale indicator here, this is a typical size of our galaxy. Okay? So these bubbles are the size, or even bigger than the size of our galaxy. And these bubbles are being created by one single black hole. So this is just how powerful they are. Now, what's really interesting is that, as you can see the structure here, this structure way up there actually represents an older cavity, okay, which has risen buoyantly. And this is exactly what we see with bubbles in water. Okay? So bubbles in water, what they do is they rise towards the surface. They just rise there, and this is exactly what we're seeing here. These bubbles just rise through the intracluster medium towards the medium that's less dense, and so they're just going to rise up. And this is what we're seeing. So this is very interesting, except we're seeing, again, on astronomical scales. So much different scales. Now, one interesting discovery that was made a couple of years ago is looking at this Perseus cluster of galaxies and looking at the X-ray emission that you're getting away from this bubble here. So these are the bubbles that we were seeing before. But if you consider this region here, and you study the kind of emission that you're seeing as a function of what we call radius, so as a function of how far you're going away from the bubble, what you see is something very interesting. Okay, you see this kind of emission. So this is the amount of X-rays you're getting, okay, as a function of what we call the radius, so the distance from the bubble as you go further away. What you see are waves, okay? These are gigantic waves, okay? These are much larger than our own galaxy, so very, very big waves. And actually what's interesting is that X-ray emission, this basically is telling us that the density of this gas is varying according to this. And it's also telling us that the pressure is essentially changing. Now, what do you get when you see waves of changing pressure? They're basically sound waves, but in outer space. And for those that, yes, exactly, okay. For those that have any talent in music, fortunately I don't at all, but this is the kind of sound that you would hear from these sound waves. So our ear cannot hear them, but just to give you a kind of indication of what you would hear. So this is really interesting things. Now you can actually see these sound waves if you play around with the image. So you have your image here of the Perseus cluster. This is another more zoomed out image of the X-ray emission you're getting, so the bubbles. This is the outer bubble I showed you. Now there's actually a lot of structure around these bubbles here. Okay? And if you play around with the image to try and bring out these structures a bit more, this is what you get. Okay, so this technique here is called unsharp masking. It's a very common technique that we use in astronomy to try and bring out all the faint features. It's actually a technique that's used also in biophysics to try and bring out faint features in, for example, MRI scans. And so this is just something that we use. And you see these beautiful waves just coming out of the cluster. And these are sound waves. And these are sound waves being generated by the creation of these bubbles as they're being created. And they're created by the central supermassive black hole. Now the question is, just how powerful are these actual sound waves and these cavities? So we see that they're gigantic, so they should be extremely energetic. And I'm going to show you just how powerful they are. And so to kind of give you an example and comparison of just how powerful, so if we take a typical energy of an atomic bomb, so this is one of the most energetic phenomena that we know of on Earth. And so we know that this is the kind of energy that one atomic bomb liberates. Okay, so we're talking about 10 million tons of TNT. Now, I'm going to show you another example, just to show you how energetic these things are. But for this example, we're going to take the sun. Okay, so the sun is very bright, okay, in the sky. It's emitting a lot of energy. Now, let's assume that it's emitting this kind of energy for its entire life, okay? So we can get an estimate of just how much energy the sun will have liberated in its entire life. And the kind of number that we get is gigantic. Okay, so there should be 28 zeros in there. Okay, and I actually looked up, and there is this number exists. It's called an octillion. I had no idea before, but it exists. And so this is the kind of energy you get from the sun. Now I'm going to show you the kind of energy you get from one single bubble created by the supermassive black hole. This is the kind of energy you get. So there's 37 zeros in there. Okay, this is known as an undecillion. Gigantic number. Okay, it's hard to conceive just how energetic this is, and all of this energy is coming from one single object. Okay, so extremely massive. So this is the kind of thing that I study. Now, what's really interesting is that I'm going to take this Perseus cluster here. So this is a very nearby cluster. This is why we study it so much, because we have such great data on it. And I'm going to show you on the same scale, okay, another cluster with another set of cavities. So this is called MS0735. It was discovered quite some time ago, but it's very interesting. Why? Because the bubbles in here, so what you're seeing is the X-ray emission, okay, in the blue. You see the radio here in the pink colors. These cavities here are the bubbles that we were seeing, very similar to in Perseus. However, this is the appropriate scale. Okay, so these cavities here are 10 times larger than the ones in Perseus. And again, these cavities are being created by one single black hole located at the center of this cluster. So just imagine the kind of energetics. And just as an indication, this little diagram here is the size of our galaxy. Okay? So this is what we're dealing with. These are the monsters. These are the biggest monsters among the monsters. This is what I study. Now, I've studied a lot of these objects here, And what's interesting is that you can ask the question, what kind of black hole do you need to be able to create such big cavities? Okay? And so what we find is that you actually need a very particular kind of black hole. And so I'm going to come back here to this diagram that I showed you earlier of what black holes look like. So this is the event horizon, which defines the radius within which nothing can escape, not even light. The size of this horizon depends on the mass of the black hole. The bigger the black hole, the larger the event horizon. Okay? What's actually interesting, and that I didn't mention, is that black holes are actually quite simple mathematically. Okay? Why? Because they are completely characterized by 3 parameters. The mass, okay, and then the other parameter is what we call the spin. The spin measures just how fast the black hole is spinning around itself. This quantity it tends to be what we call a normalized quantity. So 0 means it's not spinning. 1 means it's spinning at its maximal value. And this is related to the fact that a black hole can't spin faster than the speed of light. Nothing can go faster than the speed of light. So that determines an upper bound. Now the charge is technically, mathematically, a 3rd parameter. However, we think that all astrophysical black holes have a charge equal to 0. The reason for this is simply because when we look at the universe, we see that it's essentially largely neutral. Okay, there's nothing that tends to be charged according to a certain charge. So black holes, if one initially was created and had a charge, a positive charge, for example, it would quickly neutralize because on average the universe is neutral. So we think that essentially astrophysical black holes don't have a charge. So we're left with 2 parameters. And these 2 parameters completely determine the properties of the black hole. It determines just how powerful it can be, just how powerful it can create jets. It determines also just how much mass it can accrete, at least the maximum value. And so when we look at the big cavities here, we can ask ourselves, what kind of black hole do we need to create them? And so what we come up with is actually quite interesting, is that it seems that an easy explanation would be either that it's highly spinning, or as we'll see, it's related to the mass. And so what's interesting is that astronomers can actually measure the spin of black holes. Okay? Now this may sound weird, because how do you measure the spin of an object you cannot see? Okay? But we can do this. And the way we do this is we use general relativity. So it's very interesting, because general relativity predicts that the kind of phenomena that's going to happen related to the accretion disk varies depending if the black hole is spinning or not. So if you take a non-spinning black hole, what happens is that the material, as it gets accreted, can only accrete to a certain radius. This radius is known as the innermost stable orbit. What happens is that as soon as the material crosses this orbit, it just plummets directly to the black hole. However, what happens when you deal with spinning black holes, this innermost stable orbit changes. What happens with spinning black hole is that there's a very interesting effect, okay, called frame dragging. So spinning black holes, as they spin, they tend to drag with them space-time. Okay? And as they drag that with them, what happens is that the material gets dragged in closer to the black hole. Okay? So the innermost stable orbit here gets closer. So when we study black holes and we're looking at the X-ray emission coming from these accretion disks, what happens is that when we look at this kind of black hole, the material only goes to a certain point near the black hole. And so it gets heated up to a certain temperature. However, when we look at spinning black holes, what happens is that the material goes closer. So it feels the gravity even stronger, okay? And it gets heated to even higher temperatures. And we can actually measure the difference in temperature between these 2 systems. And this is how we can constrain just how fast the black hole is spinning. And so this has been done for about 30 systems, maybe 40 systems so far, where we've actually measured the spin of a black hole. It's been done for stellar mass black holes, so black holes in these binary systems, which are tearing up a star, but it's also been done for supermassive black holes. And we tend to see a variety kinds of spin. So they're not all highly spinning, they're not all non-spinning. It's a variety. And so astronomers are trying to understand, is there a link? Does this tell us about maybe the accretion history of the black hole? So they're trying to do this. And so the question is, for our big cavities, an easy way to create very powerful jets is if you have a spinning black hole And the reason for this is very interesting, is that actually the higher the spin, the more powerful the jets it can create. So you can create very powerful jets simply by having a spinning black hole. Now, the other possibility that astronomers have envisaged is that perhaps what we're dealing with are simply the most massive black holes in the universe. Okay? So these are extremely powerful. They're located in the most massive galaxies in the universe, which are found at the centers of these clusters. So they should have very massive black holes. And so the question is just how massive? And there have been a couple of measurements of these black holes at the centers of clusters so far. And I'm going to show you what kind of numbers you get. But before I do that, just to give you a kind of scale of how big they are. So basically, I'm going to start with these stellar mass black holes. So we know that they have typical masses between 3 and 40 times the mass of our sun. Now, recalling that the size of the black hole, so the event horizon, so the radius within nothing can escape, not even light, is given by this equation here. What you get for stellar mass black holes is that their size is essentially the size of the Bay Area, approximately. Okay? So big, but not that big. If you take supermassive black holes, okay, and we saw one example of a very famous one located at the center of our galaxy called Sagittarius A star, we saw that the mass of this black hole was about 4 million times the mass of our sun, so significantly larger. So if you plug this into this equation, what kind of size of the black hole do you get? You basically get about 12 million kilometers, which is approximately twice the size of the sun. So you have 2 suns that fit within this black hole here. Okay. And now for the biggest black holes. Okay, so the biggest black holes that we've measured so far, so the masses, are about 10 billion times the mass of our sun. Okay, so gigantic black holes. They're about 10,000 times bigger than the black hole at the center of our galaxy. This is the kind of measurements that we get. And 2 of these gigantic black holes are located at the centers of clusters of galaxies. And so just to give you an idea of what this kind of scale means, okay, so this is the size of the black holes. What I'm plotting here in this little arrow here is Neptune's orbit. So basically, this black hole is several times the size of our solar system. It's humongous. All this huge, huge black hole, several times the size of our solar system. It's very hard to envisage just how big it is, but it's huge. Okay? And so these are the monsters among the monsters. These are the really gigantic black holes. And we know of at least 4 of these that exist in outer space. And 2 of them are at the centers of clusters of galaxies. Now, I'm going to, just to finish on that bang, I'm going to end here. I will take questions, but I just want to let you know that there are a couple people here that will also gladly answer questions. And so they're all wearing helmets. Okay, yes? So there are 3 of them here today. Unfortunately, one had to cancel due to an emergency. But essentially, there's Irina here. I will try to pronounce her last name, Zuravleva. She's actually working on clusters of galaxies, and she's finding very interesting results concerning the outskirts of clusters and concerning the sound waves that I showed you. And so do ask her questions after the talk. Andre here is a graduate student at Stanford. He is also working on clusters of galaxies, and it's very interesting. He's actually published a Nature paper, so this is a very prestigious journal. Published a Nature paper earlier this year concerning a very interesting result about clusters. So do ask him questions, too, about this paper. And there's finally Sam Skillman. So he's the theory guy. He's the guy who simulates what we think is going on with the physics of clusters, collides clusters in simulations. So he's the theory guy. So please feel free to ask him questions, too. And I will stop here.